This screencast will cover voltaic cells. So in spontaneous oxidation reduction reactions, also called redox reactions, electrons are transferred and energy is released. So if we look at this reaction, we start off with zinc, metal, and in solution with copper ions. So if you blow up and we're able to look at the atoms, this is what it looked like. This would be your zinc, and these are your copper plus 2 ions in solution. When they react, the electrons go from the zinc, neutral zinc, to the copper atom, forming the copper metal, and the zinc goes into solution. So you will actually lose mass on the zinc rod, and you'll see the buildup of copper on the outside. Okay, and as time goes, you should notice that this blue gets less intense, and if you let the reaction go long enough, it will actually go to colorless. All right, so it releases energy. We can harness that energy and make that energy do work if we can make the electrons flow through an external circuit. So we set up this kind of cell. This is one half of the cell, this is the other, and they're actually called half cells. They're connected by a semi-permeable material, and the whole thing is called a voltaic cell. Okay, and a typical cell looks like this. The oxidation occurs at the anode and the reduction occurs at the cathode. The important things to label in a voltaic cell is the cathode, the anode, okay, and these are metal strips in solution, the direction of the electrons, okay, through a voltmeter, the directions of the ion in this salt bridge. The salt bridge is sometimes just a string that has been soaked in ionic compound. The idea is you're setting up a closed circuit in this voltaic cell that the electrons will travel. The electrons will travel through the external circuit from the anode, at which is the oxidation occurring, through the voltmeter and to the cathode. The cathode is where the reduction occurs. So this is going from the ion, Cu plus 2 ion, with the 2 electrons going to make the copper metal. The zinc bar is losing electrons, those electrons going in the external circuit, to make the zinc ions that go into solution, and then the 2 electrons, again, going in that external circuit. The negative electrons travel this way. That means the anions are going to travel this way to complete the circuit, and the positive cations actually travel in the reverse direction. Sometimes it's difficult to remember where the oxidation and the reduction occurs. We remember red cat and N-ox. Anode, oxidation, reduction at the cathode. For a voltaic cell, the cathode is represented with a plus sign. For the anode, it is a negative sign, and you'll see those here. So given a blank piece of paper, you should be able to draw an entire voltaic cell. Metal strip at the anode labeled negative show the direction of the electrons through the external circuit. To the cathode metal strip, they can also be inert material like graphite. Okay, cathode is a positive. You draw the beaker with the fluid in it, beaker at the anode with the fluid in it, and then the salt bridge. Okay, so all of those are important components of the voltaic cell. Once even one electron flows from the anode to the cathode, the charges in each beaker would not be balanced and the flow of the electrons would stop. That's the reason for the salt bridge. Okay, it's usually a U-shaped tube. You can use a string that's been soaked in ionic solution. And again, the cations move towards the cathode, anions move towards the anode. Okay, here's an example. You should probably do this in class. So let's talk about one of the reasons for this electromotive force. There's supposed to be a picture of a waterfall here. And the idea is, just as water only flows one way in a waterfall, if I have a waterfall, I don't draw waterfalls very well. Waterfall. Water only spontaneously flows one way in a waterfall. Okay, likewise, electrons only spontaneously flow one way in a redox reaction, and that is from a higher to a lower potential energy. Just like water falls down, electrons are going to flow from a higher potential energy to a lower potential energy. And that potential difference between the anode and cathode of a cell is called the electromotive force, the EMF. It is also called the cell potential, so relating it back to that voltaic cell, and it is designated by a capital E with the subscript cell. So this is the potential, the amount of energy that we can get out of a voltaic cell. Cell potential is measured in volts. It's important to note that 1 volt is 1 joule per coulomb. And you will see standard reduction potentials for different half reactions. These are not things that you would need to memorize, but you need to know how to read a chart and predict what would happen. So all of these are really experimentally defined. Using what's known as the hydrogen standard electrode as the reference point. Okay, and that is set to 0. Everything else is experimentally tested against this half cell to see what its potential is. So standard hydrogen electrode, those values are referenced to a standard hydrogen electrode, also known as a SHE. So by definition, the reduction potential for hydrogen is 0 volts, and this is taken at standard conditions being for any solutions at 1 molar, any gases at 1 atmosphere. And this is what the standard electrode potential, or the standard hydrogen cell, looks like. You should be able to draw this from memory as well. Oh, you know what I didn't mention in the standard conditions is 25 degrees Celsius. Okay. So in a standard, in the hydrogen half cell, and this is only the half cell, we have 1/2 of a salt bridge. This would be going to the other half cell. We have a platinum wire connected to platinum metal in a 1 molar acid solution. This is an upside down glass container where the hydrogen gas at 1 atmosphere is let into the system. What this does is it sets up an equilibrium between the hydrogen gas and the hydrogen-hydronium ion. Okay, and then depending on what the potential is on the other half cell, it will drive this hydrogen cell one way or the other. Okay, so it can go and make hydrogen gas, or it can go and make more H+. So they connect this. This is probably a better picture of the hydrogen half cell with the platinum electrode, hydrogen gas coming in here. This is a solution of 1 molar acid connected by this voltmeter. You see there's this zinc strip, that would be the metal in this half cell, with a solution of zinc plus 2 ions in the solution, and there's the salt bridge connecting the two to complete that circuit and the negative charge movement. So all electrode potentials are written in terms of reductions, meaning if the metal is reduced, the electron potential is plus, meaning the reduction is favored. If the metal is oxidized, meaning it loses electrons, the electrode potential is negative, meaning that oxidation is favored. All right, the more positive a potential is, the more likely it is to be spontaneous, or the more spontaneous it is. So when two half cells are connected, the more negative cell potential is more readily oxidized. The more positive, the more readily reduced it is. Okay. These are typically written as reductions. Okay. If I reverse them, the sign changes. So if I reverse this, the potential would change. I don't like to do them that way.